In the last section, we made it pretty clear what our utmost goal is in this chapter, and just be able to understand how to compute the important scores of web pages in the World Wide Web. Specifically, we want to understand what makes one web page more important than another. And the concept of importance is going to be recurring many times throughout the future sections. But first, before we can understand how these computations are done, let's step back and think about some of the terminology that we talked about in the last section. Specifically, we mentioned the idea of a hyperlink. So hyperlinks, we typically use those in everyday speech even. And we refer to them as when on one page you have a reference, an external link connecting to another page that you can just click on and follow. So for instance, if we had on this page a reference to www.wikipedia.org/wiki/algebra, we would, if we had a URL on this page, directly clicking there, then we would basically be establishing a hyperlink from our page to this Wikipedia page on algebra. And we could represent that using a line. And we want to put an arrow on that to indicate that we are going here, not necessarily the other way around. So again, the strict definition of a web page is a reference to some external data that's not on our current page. And hyperlinks are really important because they allow web pages to connect to each other. And that was really important in the creation of the World Wide Web. Specifically, that last part is the idea of a web. You can think of that like a spider web. So the idea is that we have billions and billions of pages that have hyperlinks in some way or another to one another. And these web pages, basically, as we said, form these connections, and we can view that sort of as a web, especially as it becomes much more and more complicated as we have more and more links. Obviously, we can't draw billions and billions of web pages on a single page, so we'll have to deal with examples in the orders of 5 or 10 web pages, but still the same ideas apply. So this brings us to the idea of what a web graph is. So what do we mean when we say the term graph? Are we talking about a graph of some function on an xy plane, where we have some sort of parabola or something that we're trying to graph here? Well, that's certainly one type of graph, but it's not the type of graph that we'll be discussing in this section. When we say graph, we mean a mathematical object, which consists of a set of nodes, which are represented as circles, that are connected by links, which are represented as lines with arrows. Depending on which nodes are connected to where, we will have these links. So in a web graph, our nodes and our links have special meaning. So each web page becomes a node in this web graph. So these nodes right here, we look at as web pages. And the hyperlinks are the links that connect these web pages together. Hyperlink. And it's important to note that a web graph is going to be directed. And the best way to understand that is if you think about your Facebook page, maybe your favorite artist also has a Facebook page. And maybe you make a reference to him. You share one of his links. We can draw an arrow this way. That certainly does not imply that your favorite artist has a reference on his page to your page, because he probably doesn't even know you. So it's important that we realize that web graphs are always directed. And it means that an arrow pointing from one page to another indicates that this one page points to this page. And it could be that it's also the other way around, in which case the link becomes bidirectional, but it's not always the case. So here's an example web graph that we'll be playing around with throughout the rest of this chapter in order to illustrate some of the computations. So here, for instance, we have 4 nodes, or 4 web pages. We have a series of 8 links. These are the hyperlinks that connect them. So for instance, node 1 has hyperlinks to 2 and 3. Node 2 has hyperlinks to 3 and 4. 3 has only one hyperlink, directly to 4. 4 has hyperlinks to 1, 3, and 2. So let's just think about this intuitively for a second. What makes a page important? Which one of these pages is most important, and what makes it the most important? Well, we need some sort of a metric in order to look at that. So one possible metric that we could look at is the idea of in degree. So in degree is basically just a count of the number of incoming links that a node has. So in the case of a web graph, it's the number of hyperlinks to that specific node. Or you just look at the number of arrows that are pointing to the node. So page 1 has an in degree of 1 because only page 4 points to page 1. So it has an in degree of 1. Page 2 gets a link from 1, and it also gets a link from 4. So that has an in degree of 2. Page 3 gets from 1, gets from 2, and gets from 4. So it has an in degree of 3. And finally, page 4 gets from 3 and also gets from 2, which gives it an in degree of 2, which is the same as node 2. So if Google was going to use this to rank its web pages and display an ordered list in the search result page, it would first print 3, since that has the highest in degree. Then it would print either 2 or 4, as they tied. And then it would print 1, since that has the lowest in degree. This would be the page displayed in the output. But we're kind of missing a pretty important idea here. And that's really what Google decided that they would take into consideration. The problem is that if we're a node, all of our links are going to mean different things. Some links are going to be more important than others. For instance, if you somehow had your favorite artist pointing to you, this link would be worth a lot more than a link just from some other random person. So we have to have some way to weight this in degree notion by how important those other pages are. So each page's importance is going to be determined in some way by the importance of the pages that are pointing to it. So if I'm pointed to by 3 pages, that could be great. But if those are not 3 pages that are important, then I might not be very important as a result. But if I get pointed to even just by 1 page, and that 1 page happens to be very important, that can make me also very important. So we can't really just use in degree as a notion of importance. We have to come up with something else. So the way Google thought of this at first was in terms of a random surfer. So what do we mean by a random surfer? Well, suppose you're sitting at your computer and you start on some web page. And based on that page, you decide to click on some of the hyperlinks from that page. Suppose that page has 2 hyperlinks. So we have connection here, connection here. So you're here right now. So if you're going to choose one of these 2 links randomly, then each of them has half of a chance of being selected by you. So suppose you migrate over and choose this link right here. So now you're on this page. Now maybe this page is connected to the other page we're talking about. Maybe it's connected to some page out here. Maybe it's also connected to another page. And then if you're going to choose one of those at random, you have 1/3 of a chance of choosing any one of those. And maybe you go and choose this one over here. And then maybe this page only points to our initial page, and so you'd come back and come back here again. And you can imagine that this process would keep going on, and we'd eventually get to a very wide range of nodes and visit certain nodes many times. And the ones that we're visiting more would be the ones that are more important. But sometimes in this process, we might also get kind of bored. So if we're surfing YouTube links, and we're surfing on YouTube, and we're clicking on links or related videos, we could really get kind of bored of that after a while. We may decide to just enter something else into our URL browser. And so if we enter some random page, it means we're going to end up somewhere random, having nothing to do with where we just were. And then that page may in turn point to some pages we've already seen before, may point to a whole other set of pages. And so Google's idea is that an important page should be one that is visited frequently by this random surfing process. So it's one that's likely to be landed on. And the more likely it is to be landed on, the more important it is. And so this takes into consideration ideas that we were talking about before. For instance, if I'm a node or if I'm a page and I have another page that's very important and likely to be landed on, and I'm the only page that this page points to, then I'm going to be equally as likely to be landed on, because when someone gets to this page over here, you know the next step is going to be me. And on the other hand, if this is an important page and it's splitting among 2 pages, then maybe I'm only going to receive half of that importance score, as we just said, because that would split in half, the probability would split in half. And these are the ideas that we'll look at in the remainder of this section. So, we can pretty easily depict the idea of spreading importance based upon that random surfing concept that we just talked about. So the best way that we do that is by first, in this graph, we'll label each node by their importance score. So page 1's importance score will be P1, P2 for page 2, P3 for page 3, and P4 for page 4. So now, as I said, if we started on page 1, then our next step is either going to be page 2 or it's going to be page 3. And each one of them would have half of a chance of happening. But we're not necessarily going to be on page 1 to start with. So we have to also weigh in the probability that we were on page 1 to begin with. And to do that, we just multiply that 1/2 by P1. So we're taking P1's importance score and we're spreading it to these 2 nodes, half each. We can do the same thing with P2's importance. P2 points to P3 and P4, so it's going to split halfway between these 2. P3, the case is much simpler actually, because node 3 only points to node 4. So it spreads all of its importance score to node 4. And if we look at node 4 and look at these out degrees, these outgoing links, we have 3 of them. So if we were on page 4, we'd have a third of a chance of visiting pages 1, 3, or 2, and then we weight that by the importance of page 4. P4 over 3, P4 over 3. So now, from this graph, it's actually very easy to equate the importance scores in the PageRank algorithm to one another. So we start at each node, and we equate that node's importance to the total importance that is incoming to that node. So we'd say, for instance, the importance score of page 1 has to be the same as this incoming link, whatever the importance of this link is, plus nothing, actually, plus nothing. It's just whatever the importance of this link is, because there's no other incoming links to P1. So P1 has to be equal to P4 over 3. Now we can go to node 2. We look at the incoming links to node 2. So we have 1/2 P1 and we have P4 over 3. So P2 equals 1/2 P1 plus 1/3 P4. And P3, the importance score of page 3, 3 has the highest in degree, so it has the most incoming spread of importance score, not necessarily the highest importance score, but it has the most terms that are determining its importance score. We have 1/2 P1, 1/2 P2, and 1/3 of P4. So P3 is 1/2 P1 plus 1/2 P2 plus 1/3 of P4. And finally, P4 receives from P3 and also 1/2 of P2. So it's going to be P3 plus 1/2 P2. So what we've basically done here is we've equated each node's importance by the sum of the importance that is spread to it by those hyperlinks that point to it. So we're taking into consideration the importance of each node that is pointing to a given node, and using that rather than the in degree to determine the node's importance. So now, we have 4 equations here, and we have 4 unknowns. So if we remember back to our algebra, we can solve a set of simultaneous equations to get the answer to this problem. And that is what we will focus on in the next segment.